Here's a video on rotation, another type of transformation. And here's the definition. If a point Q is not point P, then the rotation image of Q about point P through an angle of x degrees is a point Q prime, such that QP equals Q prime P, and measure of angle QP Q prime equals x. That is a mouthful, and so let's give a bit of explanation to that. Let's say that we are rotating about point P. So this is the center of the rotation. And the point we're rotating is this point Q. And the idea is that the image of Q is going to be the same distance from P that Q is, and the angle that's formed as I go from a point to the center of the rotation to the image, that's the magnitude, that's the angle of the rotation. So if we're rotating this Q, say 25 degrees, let's make it 45 degrees, then that's maybe about yay much. So this would have to be 45 degrees, and then Q prime would be over here somewhere, such that these distances would be the same. So the sense of it is that this thing is sort of turning around as though on a hinge, in a sense. But the formalities of it require that we say that these distances are the same and that this angle is whatever the magnitude of the rotation was. If the point that's being rotated is the center of rotation itself, then it doesn't go anywhere. And we're going to adopt a convention in this chapter that all of the rotations are counterclockwise. So this style of rotation is the only one that's going to be in play. You can't, we're not going to bother to construct a rotation, but we are going to bother to see how it works to make a fairly careful drawing of a rotation. So I'm going to rotate the line segment AB around the point Q. And so the first thing I'm going to do is to draw a little segment from A to P. And my next task is going to be to create a 45-degree angle. And the thing that keeps this from being construction is that I'm just going to use a protractor to do that. So I'm going to place my center of my protractor on P. I'm going to look for a 45-degree angle. That's about here. Sketch this very lightly. And then I want the image of A to be somewhere on this little line. And I want it to be just as far from P as A is. And if you want to be a little bit fancy about that, you can use your compass to transfer the length, but it's perfectly good, I think, just to use a ruler. And so there's my first image, and it satisfies the definition of the image point being just as far from the center of rotation as the pre-image point, and the angle between those 3 points with the center of the rotation at the vertex is, in this case, 45 degrees, since that was what we said we wanted for the magnitude of the rotation. Now, I'll just do the same for point B. So from B over to P, and get a 45-degree angle there. And so, and transfer this length. These pictures start to get a little busy, unfortunately, but so there's my B prime, and again, from B to P is the same distance as from B prime to P, and there's a 45-degree angle that runs from B to P to B prime, and now having done all that work, I can connect the dots, and I can say, all right, that is the image of segment AB under a 45-degree rotation around P, and hope that you're able to imagine that as having moved in that fashion. All right. Suppose we want to rotate a point 90 degrees. So, and suppose we want to do it around the origin. So we need to go like so, and we need to go like so, right? Because origin is the center, then we need to have this kind of situation where that's a 90-degree angle if we want a 90-degree rotation. And then we want this distance to be the same. So I'm even going to, normally you have to do this when you're playing with coordinate systems, but just for the sake of a So the image of xy is over here somewhere. And now let's think about what's going on with its coordinates. I'm going to claim that these triangles are congruent. And I'll leave it to you actually to figure out why they are. But I'm going to claim that they are, which means that this length is equivalent to this length is equivalent to this length. And so if I look at coordinates of this image point, it's going to be basically a reversal, but also, although the y-coordinate is still positive, the x-coordinate is now negative, and adding slightly to the confusion, the x-coordinate is called y. So the image of xy under a 90-degree rotation around the origin is the point opposite of y, x. So we would denote that by saying xy goes to opposite of y, x. Oops. Open bracket, parenthesis. Now, what about a matrix? We had matrices for reflections. Can we get matrices for rotations? The answer is yes. I would need a matrix, if I were going to go that way, that would allow me to multiply xy, multiply by xy, and turn it into the opposite of y, x. And as you may have gathered from the previous video, the trick is just to get the ones and negative ones and zeros in the right places. So if I have to multiply a row by xy and get opposite of y, I need a 0 so that I ignore the x, and I need a negative 1 to change the sign on the y. And so if I do that product, that's 0 plus the opposite of y. And here, I want to switch positions, but I don't want to change the sign. So I'm going to say that it's going to be a 1, 0. And then if I do the multiplication, I have x times 1 plus 0 times y, which gives me x in the bottom row. If I wanted to do a 180-degree rotation, I would have the option of doing a 90 and another 90. And one way I can do that is to just multiply the matrices for two 90-degree rotations. That should give me a matrix for a 180-degree rotation. And so I'll just take this thing, multiply it by itself, and see what comes out. And I get, this is good practice too, 0 plus negative 1, 0 plus 0. Down to the bottom row, 0 plus 0, and negative 1 plus 0. And you can go through, by the way, this will also tell you what has to happen to the coordinates. Because if I take this matrix and multiply it by a generic point xy, I get opposite of x, opposite of y. And so the description of a 180-degree transformation must be that xy is mapped to opposite of x, opposite of y. Now, one can, in similar fashion, figure out the matrix for a 270-degree rotation. I could just take 180 times 90. To save a little time, I'll tell you for free that a 270-degree rotations matrix is going to look like this. It's going to be 0, 1, negative 1, 0. And if I were to multiply that by xy, I would get, let's see, 0 plus y and opposite of x plus 0. So it should be the case that a 270-degree rotation takes xy to y opposite of x. And finally, a 360-degree rotation, that's going to take me back where I started. And so that better be sending xy to xy. And I'll tell you for free, you can show yourself if you doubt that matrix 1, 0, 0, 1 will be a matrix that will be a matrix for a figure unchanged. Let's do an example, and let's make it an example of a 180-degree rotation. And so I look up the matrix for 180-degree rotation. I find that it's negative 1, 0, 0, negative 1. I multiply it by the matrix for the vertices in the figure, so I have in ABC order 1, 1, 1, 4, and 6, 4. product, I have -1 plus 0, -1 plus 0, -6 plus 0, 0 plus -1, 0 plus -4, and 0 plus -4. And so the claim is the rotation image of this thing 180 around the origin ought to take A to A prime at -1, -1. It ought to take B to B prime at -1, -4. And it ought to take C to C prime at put that in the wrong place. No, I didn't. -1, -4. And finally, -6, -4. It's there. If you apply a little imagination, you can see that thing sort of spinning 180 degrees around the origin. And that concludes our example.